In this video, 3 examples will be used to demonstrate different aspects of the element ID module. In the first example, we will analyse an unknown spectrum that was acquired using an EMU spectrometer. So if we load the spectrum, since this is a single spectrum and no maps will be generated, the map panels are not shown in the main window. Firstly, we need to configure the analysis parameters. Since we don't know anything about the composition of the sample from which this spectrum was acquired, we will select all the available elements for identification. Also, as this spectrum was acquired using an EMU spectrometer, we need to make sure that the spectrum type is set appropriately. Changing the spectrum type will change the reference emission lines used during the identification process and also some of the default analysis parameters. Notice, for example, that the value of peak match tolerance is now 0.02 nanometers compared to 0.2 nanometers set for the Avantis spectrum type. Also, the reference window width has been reduced from 5 nanometers to 1 nanometer. Once the configuration parameters have been set, the analysis can be initiated by selecting this button in the toolbar. When the analysis is complete, the elements identified are displayed in the results table on the right. In this example, calcium, chromium, iron, potassium, magnesium, sodium, nickel and titanium are identified in the spectrum. The reference emission lines for each element can be displayed and the results of the automated analysis checked by left-clicking on each element name in the table. For example, if we select calcium, we can see that the 3 primary reference emission lines were found in the spectrum. In the case of chromium, all 5 of the primary reference emission lines were found. The emission lines for all elements can be checked in this way if necessary. For example, if aluminium is selected, we can see that the algorithm detected only 2 of the 5 primary reference emission lines. However, it is obvious from the reference panels that at least 2 other reference emission lines are also present in the spectrum. This one and this one. We can identify why the algorithm didn't identify these peaks from the information displayed in the panels. The minimum peak intensity set in the configuration is 2000, as indicated by the horizontal purple lines on each graph. And the intensity of both peaks is below this minimum value, the actual values being displayed in the information below the graphs. In this case, the user can manually change the result for aluminium. So if we click in here and type yes or Y, we can update the result. Alternatively, the minimum peak intensity value could be changed and the spectrum reanalyzed using this new value. Note though that the minimum peak intensity value is used to filter noise and spikes in the spectrum. For example, if a very low value is set, say 200, and the spectrum is reanalyzed, more elements are identified as being present. However, if we check, for example, the ytterbium emission lines, it is obvious from the reference panel graphs that the minimum peak intensity has now been reduced to the spectrum noise levels, which leads to the software erroneously identifying peaks in the noise. It is the responsibility of the user to set this parameter to a sensible value according to the quality of the analysed spectrum and to check the results determined automatically by the algorithm. If we now load a second example spectrum, and reset the minimum peak intensity to a sensible value, and then analyse this spectrum. We can see in the results table that both calcium and magnesium are identified as being present, but they are labelled with an asterisk, and the cell background colour is a darker shade of green. This indicates that those elements were found using the secondary reference emission lines. For example, if we check the reference emission lines for calcium, we can see that the three primary emission lines are heavily self-reversed, and as a result the algorithm was not able to detect them as valid peaks. In such cases, the algorithm also checks the secondary reference emission lines, and in this example those secondary lines are found, and thereby calcium is identified as being present. So these are the secondary lines, and there are more of them, and they're all identified as being present. In the third and final example, we will show when and how the wavelength shift parameter can be used to fine-tune the results found by the element ID module. So if we load this new example spectrum, and again use the default analysis configuration parameters to analyse it. Initially, aluminium, carbon, magnesium, nitrogen, sodium, oxygen and silicon are identified as being present in the sample. If we have a look, for example, at the aluminium emission line, we can see in the reference panels that the peaks in the spectrum are shifted to the right compared to the reference emission line wavelength indicated with the red vertical line. So there's a slight offset between each peak and the reference emission line wavelength. It is therefore evident that the spectrum needs to be shifted. We can do this by opening the configuration window and entering a shift value, and we'll use 0.015 nanometers. After we press enter, we can see that the peaks in the spectrum now match more closely the theoretical wavelengths of the reference emission lines. Once we have corrected the spectrum shift, we can then reanalyze the spectrum to see if the algorithm is able to find more elements. We can now see that additional elements are identified as being present as a result of adding the wavelength shift.